get started. Welcome, everyone. My name is Rob Fitzpatrick. I'm with White Star Software, and this is OpenEdge Database Internals. At White Star, we've been working for over 30 years with our customers to help them manage and monitor the best business applications. We are the makers of ProTop, and we help you monitor and alert all of your OpenEdge solutions. So here's our agenda for today. I'm just going to give a brief intro, and then I'm going to talk about the hierarchy of storage in the database, both from a physical perspective and a logical perspective, and define some terms. I'm going to go over a little bit of the history of storage and how it's evolved in the database over the years across releases. Then we'll get into the various block types that you'll find in the database. We'll look at the structures within them, the block headers, and the fields that make those up and what they mean. And then we're going to look at some of the block types in the database, especially the more common ones, and look at their contents. So as we go along, if you have questions, please raise your hand. Don't wait to the end. If I say something that you believe is wrong, I mean this, please call me out, Dimitri. That way we can all learn. And I'd like to thank George Potemkin, who provided some valuable input for this session. So why are we here? I decided to do this talk because when I started with the database about 14 years ago, I just got thrown in. I didn't have any formal training, and there were lots of lingo flying around my company about areas and extents and DB keys and rec IDs and clusters and blocks, and I didn't know what any of it meant. I was completely clueless. And this is a collection of some of the information that I've learned over the years that I wish I had known then. So I'm trying to pay it forward. And also I believe, and I've encountered, that when people don't have a common language to speak, especially across domains between development, architecture, database administration, it makes it harder to solve problems. So when we all have a basic understanding of this stuff, we can collaborate together more effectively. A few things in here are what you might classify as trivia, but I do strongly believe that almost all of this is really essential work knowledge for the working DBA, but not just DBAs. If you're a developer writing data access code, if you're a developer who's designing schema, then I think it's essential that you have some understanding of how data is written in the database so that you can understand the implications of your design decisions. Do we have anyone here who's not a DBA? All right. Do we have anyone who is? Wow, quite a mix. That's cool. Welcome. So let's start with the physical storage hierarchy. We know that databases have storage areas, and they're made up of files that we call extents. This is going to be a review on the first part, so bear with me. Just want to make sure we're all on the same level. Most areas can be made up of more than one extent, although there are a couple of exceptions to that. The control area and the AI areas are each one extent. And an extent is a collection of units that we call blocks. So the AI and the BI areas have their own block size that you can configure, and every other block and every other extent is the same size that we call the database block size. You choose this when you create the database, and then it's set. And blocks are the fundamental unit of disk I/O in the database. We don't read any less than one block or write less than one block. Every block has an attribute called a block type, and that determines what type of data is stored in there and what the layout and structure is within that block. So for example, index blocks or IX blocks store index entries. An index entry comprises some metadata plus a key value and the row ID or row IDs of the associated records. And record or RM blocks store record fragments. Note I didn't say records. So records are a logical structure that exists in, say, a record buffer in a client or a server, whereas record fragments are pieces of records that get stored in record blocks. And every record is made up of one or more fragments. If it's one fragment, we call it unfragmented. If there are two or more, we call it fragmented. Every record fragment has a logical address that we call a row ID, And that row ID for the record, specifically for the first fragment of a record, remains constant for the lifetime of that record. This is a diagram you may have seen before, so it shows just some of the area types that you might find in an OpenEdge database. There are 3 of them that you're always going to have, which are the control area, the schema area, and the BI area. The others are optional based on how you configure your database. The areas and extents are described in a pair of system tables called _area and _area extent. They live in the control area, and there's an obvious parent-child relationship between them. And that data is populated when you create the structure with a prostruct create or when you update it with a prostruct add. I'm kind of zipping through this because I'm hoping most of this is review for everybody. So in the logical hierarchy of the database, we have storage areas, and every area has a variety of attributes, one of which is the area type. And we've got a table here of the 4 area types in the database. So type 3 is the BI area, so that's the database's undo redo log. Type 4 you probably won't have is the transaction log. It's only in your database if you use two-phase commit. Anyone here use two-phase commit? No, I don't think so. Type 7 is the after image areas, so that's the recovery log for the database, and everything else is what I call a data area. That's not an official name, that's what I call them. It's not a great name, but I can't think of a better one. And these are the areas that either do contain or could contain storage objects, that is, the physical storage of tables, indexes, and logs. And it's these areas that are going to be the focus of this talk. But what about type 1 and type 2? Why aren't they in this table? Well, I guess because naming things is hard. Those aren't actually area types, and we'll get into that. More on the logical hierarchy, the 2 other important attributes of an area are the records per block, or RPB, and this is the maximum number of record fragments that can exist in a record block within a given area, and that's stored in a field called area rec bits. It's actually stored as the exponent of RPB as a power of 2. So for example, if RPB is 32, area rec bit stores 5 because 2 to the 5 is 32. And then there's the blocks per cluster, or BPC, also called the cluster size. And this is only relevant for type 2 architecture data storage areas, which we'll talk about a lot later. And all of these areas have a cluster size of either 8 or 64 or 512. And that's sort of what defines whether an area is type 1 or type 2. If the cluster size is 1, then it's defined as type 1. A cluster is a logically contiguous collection of blocks within an area. Logically contiguous meaning they have sequential addresses. And we'll talk about those addresses in a bit. And a cluster is the allocation unit for a storage area. That is, every storage area comprises 1 or more clusters, specifically in type 2 areas. And here's a little diagram of a line item from a structure file. So the number after the comma is the RPB. The number after the semicolon is the BPC. Every block has a logical address that we call the DB key. And the DB keys are sequential and increase by an amount of RPB from one block to the next. So as you can see here, we have an example. If an area has an RPB of 32, then the blocks are going to start at 32, 64, 96, etc. They'll go up by an amount of RPB from one block to the next. You can also use this feature to calculate the logical block number of a block by dividing DB key by RPB. So for example, 128 divided by 32 is 4, and that's the 4th block in the area. Okay. Also, if you know the row ID of a record fragment in a block, you can derive its DB key just by zeroing out the low order bits. So algebraically, it looks like DB key equals row ID minus row ID modulo RPB. So to flesh out the sort of mathematical relation between DB keys and row IDs a little more, we're going to look at an example. Sorry, this is a little small and perhaps hard to read, but I'll talk through it. So in this example, we're going to look at an area with RPB 8, that is, area rec bits is 3, 2 to the 3 is 8. And in this example, I'm going to use 32-bit addresses just because they fit on a slide better. But it's conceptually the same with 64-bit addresses. And we're going to look at a record block with a DB key of 96. So if we take that 96 and we convert it to binary, it looks like this, a 1, 1 followed by 5 zeros. So here's a list of bits in order, and this is basically what the layout of every address in this area is going to look like. So out of the 32 bits, we don't use the high order bit for addressing. It's just used for a delete placeholder when records are deleted. So really, these are 31-bit addresses. Similarly, in 64-bit areas, we have 63-bit addresses. The low order 3 bits are used for record fragment addressing within a given record block. And then everything left in between, the yellow bits, those are the block addressing bits. This helps us to understand why type 1 areas, which have 32-bit addresses, are very limited in size and also have a limit that is a function of RPB, because as you can see, if we added more record addressing bits, we would be taking away block addressing bits. So fewer addresses for blocks means smaller maximum size. So if we just take that DB key and we write it in binary, it's going to look like this. And I've put a dividing line between the record addressing portion and the block addressing portion. And because RPB is 8, we can have up to 8 fragments in the block, and they're going to have these numbers 0 through 7. That is 0 up to RPB minus 1. And the row IDs are simply the sum of the fragment number plus the DB key. So these are the row IDs that could be assigned to record fragments in this block. And if we convert those to binary, it's going to look like this. And when we express it this way in binary, we can already start to see some patterns emerging. For example, this column of bits is always 0, again, because those aren't part of the addresses. The block addressing bits all have the identical value of 1100. Makes sense because these are all in the same block. And the low order record bits all have unique values. Again, makes sense because they all have different row IDs. And another observation is that the first row ID in every record block is also the DB key because it's DB key plus 0. Okay, so now let's look at some of the differences between type 1 and type 2 data storage areas. So again, strictly speaking, these are not storage area types. They are, you can think of them as versions or generations of data storage area and the architecture within them. You should never create type 1 areas if you have the choice. If you're on V9, sorry, you're out of luck. But if you can create a new area as type 2, you should. If you take one thing away from this talk, that's it. Don't use type 1. Type 2 is superior in every way. So at a high level, a block looks like this. Every block has some common structure that we call the block header. And based on whether the architecture of the area is type 1 or type 2, that determines the header size. So in type 1 areas, we just have a small header, 16 bytes. In type 2, they're larger. They're a minimum of 64 bytes, and in some cases, 80. And there's even an exception to that I might talk about later. The payload, the stuff within the block, varies based on the block type. And the header, as I said, varies based on the architecture. And a lot of the data in here, these are multi-byte numeric fields. And when they're multi-byte, they're encoded in machine order. So if you're on x64, it's a little endian. If you're on, let's say, IBM Power Series, then it's big endian. Although there are one or two exceptions to that as well. So some of the attributes of type 1, it's the old architecture. Again, don't use it if you have a choice. It has small block headers. It always has 32-bit addresses, so you're very constrained on how large these areas can get. It limits the use of some of the more modern features in the database, which we'll talk about on the next slide. The area doesn't have any other level of storage structure other than a block, so it's just a collection of blocks. There's a bit of area metadata and then application data or system data, depending on which area it is. All of the space and storage management for the area is done globally at the area level. And importantly, record blocks in a type 1 area are not specific to a table. They could contain record fragments from any table that's assigned to that area, which is not good. So by contrast, type 2, which is the newer architecture, was introduced in OE10, has larger block headers, more fields, more metadata. It's either preferred or in many cases required for the more modern features such as CDC, auditing, TDE, table partitioning, multi-tenancy, and you can expect that list to grow in the future. All of your data should be in type 2 areas. Next time you dump and load, make sure you change your structure if you don't already have them. They're superior for scalability, reliability, maintenance, performance. I think I've driven that point home enough. They're what you want to use. They weren't completely implemented in 10.0a. They were introduced in 10.0a, but still had 32-bit addresses up to 10.1a. And then 10.1b was when they were fully implemented and had 64-bit addresses. And unlike type 1, where you're limited in size based on RPB, in type 2, the limit is simply governed by how many extents you have and the maximum size. So in theory, you could have an area up to a petabyte. And unlike type 1, storage management is done more granularly at the storage object level, not at the area level. So unlike a type 1, which is a collection of blocks, a type 2 area is a collection of storage objects, which in turn are collections or chains of clusters, which, as we said, are collections of blocks. So a storage object is the physical storage of a schema object like a table, index, or a lob. If you're using features like multi-tenancy or table partitioning, those introduce some other storage object types like table instances and table partitions and local indexes. Anyone here using multi-tenancy or table partitioning? Oh, a couple of brave souls. Okay. And then at the block at the beginning of every storage object, that is the first block in the first cluster of a cluster chain, is called an object block. The location, the DB key of that is stored in the storage object record in the object block field. It's also stored in a data structure in a type 2 specific block type called an object list block, which we'll look at later on. Okay, so let's look at the internal structure in a storage area. So at the top of the diagram, we have a typical application type 1 area, and highlighted in yellow here is the structure of the area. So it starts with an extent header block, which, as the name suggests, is the first block in every extent. Then there's an area block and an object block, and everything else from there is just determined by what objects you assign to the area and how, when you create your data. So they could be record blocks or index blocks. Typically, you might have some free blocks toward the end. There's a high watermark, which is basically the end of the address space. Any blocks above that have not yet been given an address and can't be written to, although it could expand into that area. And those are empty blocks belong beyond the high watermark. The schema area, which is also type 1, is a little bit different. Instead of an area block, it has the master block, which is sort of a compendium of a whole bunch of fields of database configuration and state information. Also, the fourth block in the schema area is always the first sequence block. So sequences, as you may know, have their definitions stored in a schema table called underscore sequence, but the values are stored in special blocks called sequence blocks. And the first one is always that fourth block in the area. There could be other sequence blocks later on, depending on how many sequences you define and your block size and your sequence size. And again, you're just going to have record blocks and index blocks similar to the above. And then finally, the control area, the .db file, also type 1, is a little bit different in that it has a special control block in place of an area block, but otherwise it's pretty similar to any other type 1 area. Now let's look at type 2, which has quite a bit more structure to it. So the first cluster of blocks in every type 2 area is reserved for area metadata. So there's no application data in it. So it begins like a type 1 area. So we've got an extent header block, area block, object block. Then we've got these 4 type 2 specific block types cluster list block, object allocation, cluster allocation, then an object list block, which is sort of a dictionary of the storage objects in the block, and then a free block. Now, this object list contains a data structure that can grow as you assign more and more storage objects to the area. So that last free block, in this case, I'm just showing cluster size 8, but conceptually 64 and 512 are similar. If this structure grows, then this free block could be reformatted as an object list block to continue that data structure. Here's an example of the first cluster of a table storage object. Type 2 storage objects always begin with these 4 block types, starting with an object block, cluster list, object allocation, and cluster allocation. And then the remainder of the cluster is filled with pre-formatted record blocks. By contrast, an index storage object only contains enough index blocks to hold the B tree, and then the remainder are free blocks. So, for example, if this was an empty index in a 512 BPC area, you would have 507 free blocks at the end of that cluster. So if you've ever looked at your DB analysis report and said, hey, I've got an awful lot of free blocks in my index area, well, that's why. Okay, a little bit of history of how storage has evolved. So in V8 and earlier, we just had all of the data in one data container, the DB file. This was type 1 architecture, 32-bit addresses, and those addresses were unique globally across the database because the database was just essentially one file. V9 introduced storage areas, so we could have a schema area and you could have application areas as well. So this changed the paradigm in that now addresses are unique to the area, not the database. And then in V10, we got type 2 areas, not fully implemented, as I said. They still have 32-bit addresses, but we do have some new structures. We have larger block headers. We have table-specific record blocks. We have object-specific clusters. And then they become fully 64-bit in 10.1b. Then into V11, we had multi-tenancy, so that introduced the concept of table instances, which are storage objects. So for the first time, a table can span storage areas. And then in 11.4, we added table partitioning. So this meant that a table can actually have 2 different records in different storage areas that have the same rec ID. So what Progress did to ensure that you have a unique locator for records is that they appended, when you get the row ID function of a record, they append the partition ID, which is a 16-bit value, as a prefix on the row ID so that it's a unique value. So if you're using table partitioning, you should avoid trying to use the rec ID function because it's not guaranteed to give you a unique value. So let's look at some block types. If you look inside one of your modern databases, every block you look at will have one of these 14 block types. They aren't all very interesting, so I'm not going to talk about all of them. Some of them are pretty easy to describe. For example, empty blocks are empty. Not much to say there. But there's some more interesting ones like record blocks that I'm going to talk about a lot. Just as a historical note, there are 6 other block types that are defined, but you'll no longer find them in a database either because they're old historical and they don't exist anymore, or they were planned for type 2 implementation, but never actually used. So we'll start off with looking at the contents of block headers, and we'll start with type 2 we'll start with type 1 because they're the simple ones. Type 1 header is 16 bytes. It's made up of 6 fields. So we've got DB key, block type, chain type, backup counter, next block in chain, and update counter. So here's a little more info on these. The DB key, again, is 32 bits. The block type is one of these numbers that we saw here. The chain type, if you saw Dimitri's presentation on Wednesday, you'll know about free chains and RM chains and index delete chains. So each chain has a number, and that number goes in this field if this block is on a chain. If it's not on a chain, there's a special value for that. 127 means no chain. The backup counter, there's a little bit of confusion sometimes about this field. People think that it's the database backup counter and then it gets written to every time you back up the database. That's not the case. That is the case in the database master block where the database backup counter is stored, but otherwise, this field in any other block in the database is only written to when there's a block write and it gets the current value of the database backup counter. And this is what facilitates incremental backups so that ProBackup knows which blocks have been updated since the last backup and which ones haven't been. So I mentioned chain type. This is where those chains are implemented. So if a block is on a chain, let's say it's on the RM chain, so this chain type field would have a value of 1, and then the next F field would have a value which is the DB key of the next block in that chain. So that implements this singly linked list that we call the RM chain. And finally, the update counter just contains an incrementing number. Every time the block is written to, it gets a new value. And these are the counter values that are referenced in AI and BI nodes that modify blocks. Okay, type 2. This should look familiar because it's just that. So the first 6 fields of the type 2 header are the type 1 header. So type 2 isn't a brand new header format. It's simply an extension of the existing type 1 header. And then in type 2, we have 12 more fields, a bunch more metadata. And you'll note that we also have a couple of duplicate fields. We have our old 32-bit DB key field plus the new 64-bit. This is what allows these areas to grow larger because they have larger addresses. And again, next block in chain is duplicated as well. And in case you're wondering if I have a block larger than, with an address larger than 32 bits, how do we write the DB key in here? We don't. It simply gets a value of -1. So we'll look in a little more detail at these headers. When the block is a cluster boundary block, that is, it's the first or last block in its cluster, it gets an even larger header of 80 bytes. And depending on its position, it'll get one of these 2 fields in each of these positions. So we'll go into these in a little more detail. The first new block in type 2 header is the block checksum. So this is a value. It's basically a CRC calculation of the data in the block. So anytime the data in the block changes, the CRC changes. And it's there basically to detect if there are problems, like if some bug caused a block to be written improperly or a file system issue or something like that. Don't think of this as a security issue that's going to prevent tampering. It won't. These are easy to spoof. Don't ask me how I know that. I admit nothing. But it's not a security feature. The next field is the header size. And because type 2 block headers are variable in size, the storage engine needs to know where does the header end and the data payload begin. So this is how it knows. So that's always going to store a value of 64 or 80. The next 2 fields, because the blocks in type 2 are specific to one storage object, this tells us what object that is. The object type has a value of 1, 2, or 3, meaning table, index, or lob. And the object ID is either the table number, the index number, or the field number if it's a lob. The next field is the DB key of the object block, which means whatever block we're in anywhere in any cluster, we can always find the head of the cluster chain because the object block is the first block in the cluster, first block in the first cluster. Next, we have the DB key and the next block in chain. BK last BI note. I don't know what that's for, so I didn't describe it. Anybody else know? No? Okay, we're all clueless. Partition ID is next. That was added in OE11. So if you were looking at a V10 block, you wouldn't have this field. It would just be zeros. If you don't use partitioning, also that field is going to be zeros. And the last field listed here is an extension of the backup counter. So in V12, Progress extended the backup counter from 2 bytes to 3. Apparently, there were some customers who were doing lots and lots of backups, and they were rolling over the backup counter at 65,535. And then bad things happen, like your backup stopped working. So there wasn't room in the existing backup counter field to put in extra bytes, so they stuffed it down here. Obviously, this field is type 2 only, so they had to come up with a different mechanism to make it work in type 1 areas, and I don't know what that is, so I can't describe it to you. The last two fields are reserved for future use, so maybe in V13 we'll see some new fields there, I'm not sure. As I mentioned, if the block is the first block in its cluster, it gets two additional fields, which are transaction ID and serial number. I don't have anything interesting to say about those. And the last block in the cluster has two extra fields called next cluster and previous cluster. So this is how cluster chains work. I mentioned earlier that a storage object is a chain of clusters. So next cluster is the DB key of the first block in the next cluster in the cluster chain of a storage object. And similarly, previous cluster is the DB key of the first block in the previous cluster. So it's a doubly linked list. So how do you look at the inside of blocks? Well, there's a utility that you all have access to on your systems. It's called DB Repair. And before you go playing with it, please be advised, it can be dangerous in the wrong hands. It has some features that are read-only and they're perfectly safe to use, and that's fine. It also has some that, if you don't know what you're doing, you can destroy your database irrevocably, and I can't help you, and neither can Progress. So if you want to play with it, great. Spin up a sports database and do that. Don't do it in prod and then come crying later. If you want to look at the block contents, you can select a storage area, option 9, and then use option 13 to display the block contents. It'll show you the headers, it'll show you the data payload, it'll break it all out and give you labels. It's neat. So let's look at some record blocks because they're the most interesting and that's where most of your data lives. A record block looks like this. Not very exciting yet, but it doesn't have any records in it. When it's empty, it just has a block header, as does every block type, and then it has this structure called an RM header, and then the rest is empty space. But when we add a record fragment, it looks like this. We get two new data structures. We get this thing called the directory entry. So that's a row directory with one entry in it. And then that record fragment that we added goes in the bottom of the block. And so the free space that's left in the block remains in one contiguous chunk in the middle of the row directory and the record fragments. If we add a second fragment, it now looks like this. We get a second row directory entry and we get a second record fragment. And as we can see, the directory grows down into the free space and the record fragments grow up into the free space until they meet in the middle and the block either becomes physically full because it's out of space or logically full because it's out of row directory entries. It should be obvious that you can only have up to RPB number of directory entries in a block. So let's look at that RM header in a little more detail. It's a small structure. It's only 4 bytes. It has 3 fields and they describe the row directory and the free space. So the 3 fields are called numdir, freedir, and free. Numdir and freedir are each 1 byte, so they can hold a value from 0 to 255. Numdir describes the highest numbered used row directory entry, not the number of row directory entries that are in use, as the name might suggest. And freedir is the number of available entries. So this is part of what the storage engine uses when it's making a decision about where to store a new fragment. And it evaluates a record block to see, could I put this fragment here? It's looking at, does it have available directory entries? Does it have available free space? And again, free just describes the amount of free space left in the block, the whole chunk, including the create limit. So the row directory is sort of a mapping layer of logical locations to physical locations. So if we think about what's in an index, what is an index? In terms of its contents, it's a sorted list of key values and their associated row IDs, right? But those row IDs are logical addresses. They just point to a particular record block and a particular slot in the row directory of that record block. It doesn't tell the storage engine where the fragment can be found physically in the block. And that's what the directory entry is for. So this is a dynamic structure. It grows on demand, as we saw. And it starts out at 0 entries and grows up to RPB number of entries. Each entry is 2 bytes long. And now we're going to look at what makes up that entry. It consists of a 3-bit bitmap and a byte offset. So The bitmap is just some metadata about the fragment. The first one is called a hold flag, and this is used if the fragment gets deleted. Remember I said earlier that the record fragment maintains its row ID for life, and life includes if you delete a fragment but then don't commit that transaction, you need to roll back. We wouldn't want to delete a fragment, have that transaction still active, and then somebody else steals its row ID, then you try to roll back, it wouldn't be able to, right? So that hold flag says, don't use this row directory entry, it's mine. Okay, so when you delete one, that bit gets flipped to a 1. The second bit means this fragment has a continuation fragment. In other words, it's a fragmented record, and there's another fragment yet to come in some other record block. We'll look at fragmented records later. And then the third bit means this is a continuation fragment. In other words, there was some stuff in the record in some other fragment previously that pointed to this one. In other words, this isn't the first fragment in this record. So that's the first 3 bits of the 16-bit directory entry. And then the last 13 bits describe the physical offset from the beginning of the block to the beginning of the record fragment. So that's the physical locator of the record fragment. Okay, so now let's look at what a record fragment actually looks like on the inside. So I'll take the simpler case here of an unfragmented record, meaning the entire record is in one record block. It begins with a 2-byte fragment length field. This is one of those exceptions that I talked about to the big endian, little endian thing. These are always encoded big endian. I don't know why, they just are. Next, we have some record metadata. This is always going to be at least 14 bytes, but it could be larger. Mike has a question.
You want to know why?
I sure do.
The records are always, which endian is big endian. The entire record format is big endian. So while it's databases are not compatible, the records as they're stored could be compatible. So everything is big endian, not just the length, but if you store it it's big endian.
Okay, thanks, Mike. So Mike is saying all of the fields, just for the recording, all of the fields in the record are big endian, whereas header fields are not. Okay, so it contains some data structures, or could contain some, like a field map, a skip table. A skip table is a mechanism that the database uses to make the selection of individual field values, if you're using a fields phrase in a query, for example, more efficient. It's sort of a lookup table for where fields are within record. And the more fields you have in a table, the larger that skip table will get. It also contains the schema version number of the table number, and the field count of the table. Interesting little note here about these fields is that the table number, for example, which is an integer, obviously, is stored in a variable length format, just like integer fields in records, which means if you have a table with a number between 1 and 127, it's going to occupy 2 bytes on disk, whereas if it's 128 or larger, it's going to occupy 3 bytes on disk. So it's something you might want to consider if you're doing a dump and load and you want to maximize your record density in your blocks, because if you have a very large table with lots of records, especially lots of small records, you could move it up in your DF so it gets loaded earlier in the load process and therefore gets a smaller table number. And if you've got, say, 100, 150, 200 records in every record block, you could be saving yourself 200 bytes in that block and have more space for records for free. So now let's look at a case of a fragmented record, in this case, a record with 3 fragments. So it may not be clear here from the diagram, but each of these fragments is going to be a separate record block. That's what it means for it to be fragmented. So it begins with a structure that we didn't see in the previous diagram, which is a next fragment row ID. So this is a pointer to where can I find the next fragment. So it's the row ID here is going to be the row ID of this second fragment. And then, And then it looks just like the example we saw before. We have a fragment length, the record metadata, and then the collection of fields, which are each implemented in variable length format. So there's a field length and a field value. In some cases, if there are certain special values in these fields, the value field itself can be optimized away. For example, if you have a numeric field, like an int64, rec ID, date, logical, under the covers, they're all really integers. If you store a 0 in any of those data types, you won't actually have a value field. You'll simply have a 0 in the length field, and that's taken to be a 0 value. So it's a little optimization that saves a byte per field. And there are some other values like that as well. If you store the unknown value in a field, it also just occupies 1 byte and not 2. And so if this were a 3-fragment record, that's what the row directory bitmap would look like. It would be a 0, 1, 0. The second fragment has the next fragment row ID, the fragment length, and the fields. And then the last fragment obviously doesn't have a next fragment pointer because it's the last fragment. And it just has the length and then the field values.
Can I make another comment here?
Sure.
So when we're doing approach to SQL and you're replicating your database from OpenEdge to SQL, we found that the SQL target size is 3 to 4 times the size of what the OpenEdge database is. This is the reason why. There's a lot of compression optimization in how things are stored in OpenEdge that doesn't exist in the other data.
Good point, Mike. An example of the optimization and the lengths that Progress went to try to extract as much value as possible from your data is, I said this is 4 or 8 bytes. In a type 2 area, all of your addresses are 64 bits, right? So that's 8 bytes. So how could this be 4 or 8? Well, if the next fragment is in a block that's below the 32-bit boundary, that 64-bit address is going to have at least 4 bytes of leading zeros. So Progress simply doesn't store it. It just stores the significant low-order 4 bytes, and it just formats it differently if it's going to be an 8-byte address, so that it can distinguish, how long is the address. Basically, if the leading bit is 1, that means it's 8 bytes. If the leading bit is 0, that means it's 4 bytes. Okay, index blocks. An index block stores one node in a B tree. So an index logically is a B tree structure, and it's made up of nodes. Every block stores the data for a node. So that could be the root block, or it could be a leaf node, or it could be one of the in-between non-leaf nodes. Each block stores index entries, and those are made up of some metadata that describe the entry and the row IDs, the key value itself, and the row ID or row IDs that correspond to those key values. There could be multiple row IDs that correspond to a single key value if the index is non-unique, and obviously if it's a unique index, it's a one-to-one relation. I didn't put a diagram here because a hex dump of an index block just looks like kind of garbage, because the index manager employs data compression in several different ways within index blocks, so they're not too fun to look at. But if you want to know more about it, Mike Fergal, the talkative guy over there, and Gus Bjorklund did a great presentation 4 years ago, 4 or 5 years ago, I think 4 years ago at Pug Challenge. It was a 2-part talk on all about indexes and the index manager and index blocks. So look it up on the Pug Challenge website in the archive. It's well worth looking at. Next, we're going to look at object blocks. Really, there are 2 types of object blocks. Every storage area has an object block as its second addressable block, third block in the area. And that contains a bit of overall space management info about the area, but also every type 2 storage object begins with an object block that has object-specific space management info. So it's got info about the chains and their state, like the first block, the last block, the number of blocks, the total blocks in the object or area, the high watermark. In later versions, you're going to have more fields. So for example, if you're looking at a 12.3 or later database, you're going to see some fields about table reorg. The payload looks something like this. Bit of an eye chart. I've just highlighted some of the more interesting fields. We've got the first the first DB key on the RM chain, the last one, the number of blocks on the RM chain, the total number of blocks in the object, the block at the high watermark, which for some reason is expressed as a block number, not an address. Don't know why. Mike probably does. And again, if in later releases, you're going to see more fields. Okay, the master block. So again, this is the first addressable block in the schema area, and it's sort of clearinghouse of different information about database configuration. I've given some examples here. So we've got the database backup counter. We've got the tainted flag. If you've ever tried to start a database and it says, this database is damaged, you need to dump and load, that's where this is stored. The timestamps that you see in a pro-util describe are all stored here. The backup timestamps for full and incremental backups, the block sizes, the BI cluster size, the last TRID, information about log archiving. Anyone here use log archiving? 11.7 and later? Great feature. You should be using it. Lets you automatically archive your database logs instead of having to script it. Info about after imaging, replication, lots and lots of other stuff. There are dozens and dozens of fields. There's no way it's going to fit on a slide, but hey, play with pro-util DB repair and see for yourself. Extent header blocks, I mentioned earlier, they're the first block in every extent. They're a little weird. They don't have a DB key, or if you like, they have a DB key and it's always 0, even if there are multiple ones of them in the same area. So really, they sit outside of the address space. They're not read into the buffer pool. They're just sort of a housekeeping block that the database uses to, ensure integrity. You can see that it contains timestamps in its payload about the creation date and last open date of the extent. It also has the DB version number, which is the sum of a DB major version number and the database block size. So in this case, 184 is the major version number for V12, and 8192 is the block size. And it always has a type 1 header, even when it's in a type 2 area. It's the only block that is like that. If you other version numbers you might see here are 173 if it's a V11 database, or 150 it's a V10. And it's going to be incremented again in V13. Sequence blocks, I mentioned those earlier. So sequence blocks are always in the schema area, thus they always have a type 1 header, 16 bytes. And the first sequence block always has a predictable DB key because it's always the fourth block in the area. So that's 192 if you're in an 8K database, and it's going to be 96 otherwise. And sequence blocks, if you have multiples of them, are chained together in kind of an interesting way. So here's a diagram of the headers of two sequence blocks from a database. We can see the first one has a DB key of 96, so this must be from a 4K database. And its next F field has a DB key value of 2336, although you can see it's not on a chain. But the next DB key, which happens to be block 74 in the area, has a DB key of 2336, and it's a sequence block. So there is a sequence chain, but for some reason, there isn't officially a chain value for sequence chain, but that's how they're linked together. Also, sequence blocks, unlike most other block types, are not demand page. They're loaded into the buffer pool when you start the database, so they're always in memory. The sequence values in a sequence block are stored in order, and unlike other integers in the database, they're stored in a fixed width format, and for good reason, because there isn't any metadata or pointer or directory that says where to find these values. They're simply found by doing the math. Every sequence is either 32 bits long, that is 4 bytes, or 64 bits long, 8 bytes. You can tell which one you have by looking at a pro-util describe, and feature 11 tells you whether you have 64-bit sequences or not. In 12, they're all 64 bits now. There have been a lot of changes in the limits over the years. In older releases, you could only have 2 sequence blocks, so the number of sequences you could define was actually governed by how long your sequences were and how large your blocks were. But now there's a standard limit of 32,000 sequences. And I think you can also have 32,000 tenant-specific sequences if you're using multi-tenancy, so it's a lot. And if we look inside a sequence block, it looks something like this. So the top half of the diagram is taken from a database with 64-bit sequences. We can see they're each 8 bytes. Each one of these sequence values in this case, has a value of 1. So you can see this is from a little endian system because the values are byte swapped. And we can see it begins with the 16-byte header. By contrast, this is a 10.1a database, so it has 32-bit sequences, so you get twice as many values per block, but there's a pretty hard limit on how many definitions you can have. I mentioned the object list block earlier. This is a type 2 specific block type. It's always the 7th block in a type 2 area, and it contains a data structure called object list block. And it's a listing of all the storage objects and some of their attributes, like the DB key of the object block and the object ID and object type. Note that there's also a line item for the area itself. That's what type 8 means. And there are pointers here to next block and previous block. So these also have chains, but again, they're not implemented in the header. They're implemented within the payload itself. And if you add more and more storage objects to an area, then this structure will grow, and it might have to grow into multiple object list blocks. In a 8K database, you can have roughly 166 line items in this table before it overflows and a new object list block needs to be formatted. Free blocks are blocks that are not yet formatted into some other block type, and they are below the high water mark of the area, and they don't contain any data, just a block header. And then I mentioned empty blocks earlier. They're blocks above the high water mark, and they don't contain anything at all. And that's about it. Do you have any questions?